Welcome to Electron. In this video, we're going to talk about the energy stored in an inductor. Imagine you have an inductor connected to a circuit and there's no current at all. There's no current going through the inductor. Then there's no energy stored in the inductor. But as you have current that's beginning to flow through the inductor, initially the inductor will oppose that change in current going from 0 amps to 1 amp. And there will be an EMF induced that opposes the change, but eventually current will flow through the inductor. And by doing that, there is an establishment of a magnetic field through the inductor that goes through the inductor and around the inductor and back through the inductor like this. As you continue to increase the current, the magnetic field will continue to build up and become stronger, stronger, stronger through the inductor and around the inductor like this. You're building up a magnetic field, and that magnetic field stores a certain amount of energy. Now, how much energy does an inductor store, and how do we calculate that? We do it as follows. We start with the power equation, where the power is equal to the voltage times the current. And of course, with an inductor, the voltage is equal to the inductance times the rate of change of the current with respect to time. Now, to find the amount of energy stored, it would be the amount of work done to develop that magnetic field. We can write this as the small amount of work done, dW, is equal to the power times dt. Remember that the definition of power is equal to work over time or energy over time. Of course, the amount of work you do is equal to the amount of energy you store in the inductor. So we can use the letter W for work, or we can use the letter E for energy. Now, to have the total work done, which is equal to the total energy stored in the inductor, we can say that W is equal to the integral of dW, which is equal to the integral of P times dt. And of course, P can be written as V times I, so this is equal to the integral of V times I times dt. And instead of writing V, we could write L times di dt. After all, the potential across an inductor is equal to the inductance times the rate of change of the current with respect to time. So this can be written as the integral of L times di dt times I times dt. Now notice that first of all, L is a constant that can come outside the integral sign, and dt can be divided into the dt here. That cancels out. So this can then be written as the amount of work done, which is equal to the amount of energy stored in the inductor, is equal to the inductance times the integral of I times di. And the limits of integration is we start with zero current and we finally reach the final current in the inductor. And so this can then be written as L times I squared over 2, and the limits of integration from 0 to final current. When we plug in a 0, we get nothing. When we plug in the final I, we get equal to 1/2 times the inductance times the final current squared. So in other words, the energy stored inside of inductor, we can either write it as W or E is equal to 1/2 the inductance times the current squared. And that's how it's done. That's how we find the energy stored in an inductor.